new big thing, and basically it is something which was advertised as a new wonderful material, which is solution for future green construction material. And Professor Davidovich from France, he was really promoting this name and this development. And the story again started not in France. Story started back in Ukraine back in 1950s, after Second World War, when construction crisis happened, and many countries were searching for a relatively cheap, affordable green construction solution which they can use for housing to resolve the housing problem. But at the time, they call them alkali activated binders. And basically, we know that these binders can be classified as inorganic binders, means they are not containing organic compounds, and they don't need organic compounds to bind. So basically, cement-like material or ceramic-like materials. And they can also have long-range covalently bonded, non-crystalline amorphous networks, which are binding everything together. So inorganic materials. And this is why we call it geopolymer, like earth polymers. And actually, the earth binders actually was another name for these binders back at the time. And again, very often these materials can harden at room temperature, like Portland cement. And sometimes they would benefit from heat treatment to initiate the polymerization reaction as well. And again, you can have pozzolanic material as a part of reaction, but in reality, you need alumosilicate products, which can be combined with alkali hydroxides. I mentioned already sodium and potassium hydroxide. Other exotic hydroxides can be potentially used, but remember, if you use just simply calcium hydroxide, it will be a classical pozzolanic reaction when you have calcium hydroxide reacting with silicon dioxide, and you have regular like CSH like product like we have in case of Portland cement hydration. So we can use also alkali silicates and also alkali carbonates. And water is important, but it is really carrier for the ions to react with and attack the alumosilicate materials. And okay, there is a story about Gluchovsky. I can skip it. I already was trying to talk about soil cement, but so you can say the soil cement is like something that's geo, and also polymer is also like maybe considered as an analog of cement. And Davidovich was basically picking up on technology which was not that actively used and was known to maybe only few enthusiasts, but he really was participating in Gluchovsky meetings, and he was really basically collaborator, I can see, because he published papers in his conference volumes. So he was involved with all the research team and with all this research community. So basically he did a great job to popularize it, bring it back to research community, and everyone was excited about the product and the geopolymer potential impact on sustainable construction. And we can speak about pozzolanic activity, and pozzolanic generally the product which has amorphous silicon dioxide, basically. Silicon dioxide, it reacts with calcium hydroxide or any alkaline substance, and it can have a material which has cementitious products. And we can speak about these components, reactive powders, which can be participating from one side. It's again mostly alumosilicates, just not simple pozzolan. It can be calcined clays, kaolinitic clays, different clays. It can be volcanic rocks as well, because those alumosilicates, some mine tailings, can be also suitable for the technology. But it can be also a large group of industrial byproducts. So we have blast furnace slag, we have coal fly ash, we can have rice husk ash, silica fume, you name it. So again, those can be pure siliceous, like silicon dioxide based, amorphous silicon dioxide based products, but can be also alumosilicate based. And again, we will post this picture so you can read a little bit more about pozzolans. And the geopolymer structure, so we have this network of silicon connecting network, and using silicon and aluminum as a bridging, bridged by the by alkalis. And the similar way we have organic structure of organic polymer, three-dimensional structure of organic polymer as well. So this is why it's called geopolymer. And again, when we look for geopolymer binder, it's a little bit different animal than Portland cement, and different from what we can see in epoxy resin. So you can see how they look under microscope. And I'm quickly go through the terminology here: monomer, oligomer, polymer, polycondensation. What, again, you can look at this. Maybe we can return back to this discussion next time, because today you will see bright side of geopolymers, but we'll try to dig and discuss more next time, and I will try to see that Marina is there, and we can bring it to discussion next week as well. So basically, we can speak about how geopolymerization is happening, but basically you have, again, from one side silicon dioxide, you have aluminate, aluminum 2-3 combined in form of amorphous product. But in case of alkalinity available, you can have, again, formation of alumina silicate gel, or zeolitic phase, which is nanocrystalline or a product. And again, this is what is possibility there. Important is you have relatively durable ceramic-like material, which can bind together and which can be used as a cementitious material. Again, different forms. You can see different compositions there. For example, here is potassium and sodium are incorporated here, but you can have also calcium and magnesium oxides coming from the raw materials as well. No problem with incorporation. You can have compressive strengths. Well, the relatively early compressive strength. So basically, you can have 25 megapascals. So if you look for DOT goal for 3,000 psi, you can easily have it say in 5 hours. In 5 hours, you can pass 3,000 psi benchmark. So it looks like attractive for repairs, like rapid curing, etc. And compressive strengths of pure geopolymeric binders, again, pure geopolymeric binders, can reach 80 megapascal at 28-day strength. Can develop further as well. Some materials are developing only 40 or 50 megapascal. So I would say, from my experience, it is not exceeding the range of Portland cement. Normally, when we test Portland cement according to different standards, you can have compressive strengths from 30 to 50 to 60 megapascal, depending on the grade, depending on the type. But if you test just neat binder, 70–80% with super plasticizer is pretty easy, because the compressive strength for cementitious systems, same as for geopolymeric systems, is function of water to cement ratio. So again, more water, less strength. But if you use less water, you may lose workability, and you may not have complete mixing. You can have clumping, and you can have issues with the product. So the beauty of geopolymers, it is really materials which can serve well in strong acids. So it is basically acid resistant, material. So if you need to have material for chemical production, which has acid spill or acid as a part of the process, because acid can be in condensation of acid, can be acidic substances on the structures. This is beautiful product. And even like some very nasty type of acids. I consulted the chromium acid production facility. The spills were very difficult to handle, and normal concrete was not just surviving there. But as soon as we use geopolymer, this material really last for longer times, and this was the solution for a chemical production facility. I think also it is important to mention that the geopolymeric materials can be also refractory materials, so they can easily serve for 700 degrees Celsius, but they can go in up to higher temperatures as well. So in this way, they work really better than conventional Portland cement in respect to higher temperatures. So check mark is high early strengths, compressive strengths at the level of regular Portland cement can be easy tuned, and also the acid resistance and high temperature resistance. So if you think about some chemical production plant, repairs on cement plant where high temperatures are required, maybe geopolymer is a perfect fit, okay? Refractory performance, again, for excellent fire resistance, And again, the geopolymers can be combined with a different type of fly ash. And again, this is what Marina can speak more, it was her research. And but there are some larger structures. Australia is one of these leaders in production of geopolymer, simply because as a person from the discussion which happened, I think, when it happened on Tuesday or Friday, sorry, not on Tuesday or Wednesday, I think it happened, discussion about the benefits of geopolymers. Person from Australia said, we produce more fly ash than Portland cement. Basically, they have to use what they have locally. And in this way, it is a perfect fit when for Australia, because they didn't invest in Portland cement. They buy most of their Portland cement from outside. Maybe Steve can share a little bit more on Australian cement industry next Friday. But we know that this is the statement from people there, from leading researchers from Australia, and basically they mastered application of geopolymer. They know where it is used, can be used, and they use it in massive quantities. So they are showing us good example when locally available byproduct is completely utilized in construction, and they claim green properties. Question is, not everything is that bright as actually happening with geopolymer. And I'm just looking if Marina has it in the slides. Okay, they have another project here is Australia again. They use it for airport construction. And okay, this is the summary which I already mentioned. Again, sometimes geopolymers, they claim to be extremely ecologically friendly and sustainable, simply because they think that, oh, geopolymer is using 80% of byproduct in the binder content, and 20%, 30% is alkalis. Question is, alkalis are not coming from the waste stream. Alkalis are highly high-end type of chemical products, and maybe we can ask Philip if he is still with the group. No, I don't see him. He lost it. Marina, are you there? I think I can see you. Can you speak? Just unmute yourself if you're muted. Oh, okay. Well, let's continue. I think we have a few more minutes left. But what I'm saying is very often we forget about source of alkali. I will ask Philip to dig on this a little bit, maybe prepare a slide or two for next week, just to understand what is involved with alkali production. And second question, if we have any chance for waste stream for alkalis, because if you have a waste stream that contains alkalis, and from another side, waste stream which contains the alumosilicate, you put them together, you match, and you have win-win type of situation when you produce suitable material. Only once in my life I've seen the waste product which contained large volumes of alkalis. It was some product which used for leather treatment. I forgot the type, but I worked with that product. But I remember it was a byproduct which was actually washed away in local river, and I just had I was not that accurate, and I just took like some of this water. I just looked with my with my head, and I just realized my fingernails were just completely whitened because they were attacked by the chemicals in the water. I just didn't realize that water can be such a polluted in that river. And it happened in China when I visited as a young scientist to help them with waste utilization project. So once in my life I've seen, and I believe it might be some in specific location, can be some waste stream which contains high alkalinity source. I would say most probably would be stupid to throw it away. Would be nice to capture it and use it for something else. And for example, geopolymer can be one of the solutions. Instead of polluting river, just use it for production of construction material. Obviously, the durability has some question. Yes, Steve, any alkali source can be used. You're absolutely right. You're absolutely right. Any source, especially if you can capture sodium and potassium from the kiln. And nowadays, I think this is not the case because we used to have kiln dust as well, which was containing large quantities of those elements. Now, again, the source of alkalis, sodium and potassium, can be beneficially, if you can separate it, we can have, you can have very ecologically friendly geopolymer. But until we don't have this, until we rely on sodium silicate or potassium silicate or sodium hydroxide and potassium hydroxide, I don't think we have a complete sustainable solution. Again, might be good for the lab. You can demonstrate, you can claim the performance, but in real life, this is why it is actually not picking up, simply because we don't have that quantities of alkalis available in production. You remember our lecture number 1 or number 2 when we discuss about resources, and we discussed with you that sodium and potassium are really like not that huge in terms of offer, but calcium is actually is there, silica is there, alumina is there, and this is why geopolymer may still have a niche application, and again, serve where they perform the best, where Portland cement siblings cannot do the excellent job anymore, unfortunately, such as high temperature application and where we have chemical attacks. Specifically, I'm saying acid attack. So where you have acid attack, this should work extremely well. I am looking for the timing, and we are almost there with last slide. Yes, she has the sources